Now we're ready to actually input some of the geometry into the fatigue crack growth tearing energy program. This program was custom written by Experimental Services to perform fatigue crack growth propagation, and I'll explain just a little bit of the features. And first we'll enter the specimen identification. We'll enter the thickness of the sample that we just measured with the calipers, the average thickness in millimeters, and we'll measure the length of the specimen. Now the conditions have already been preloaded. The program's already been set up to run strains of 5%, 6%, 7%, 8%, and 9%. We can vary the number of cycles we run at each strain. Right now it's set up to run 10,000 cycles at 5% and then 5,000 cycles each at 6 through 9%. We're ready to start the controller. It opens up the specimen just wide enough, about 1 millimeter, so that it can see that it's going to be able to get a good crack shot. And then I'll hit start pulse over here, and it's going to start to put a controlled pulse into the specimen. The conditions of the pulse are also programmable. We can program the rise time and the magnitude of the pulse. And it's counting up the number of cycles that it's actually putting on the sample right now. And when it gets to 100 cycles, it's going to stop. It's going to open the grips just slightly, about 1 millimeter, and it's going to take a picture of the specimen. There we go. It's transferring the data from the camera to the computer. And there's our first shot at our crack growth. Now it's going on. It's going to do another 100 cycles. It'll take another picture, transfer the data to the computer, and calculate the crack growth and move on. Before it actually starts calculating a crack growth rate, it's going to take 10 samples and then look back 10 samples to come up with any averages. I can set things like the processing area for the camera to really zoom in on the end of the crack so that we're not using too wide a processing area. We're just got the crack very closely confined with the image. Some other things that we can do are we can take a look at the control loops on the controller, and we can adjust the control loops, the PIDs, so that we have tighter control of conditions. But actually, this specimen is set up to run 4% strain, and you can see how tightly it's controlling 4% strain, basically the second decimal place. It gives us a peak load in newtons of the pulse and also the valley, and then calculates the modulus and some other features. The specimen's actually under test right now. This is at a 4% strain level. It's going to conduct 100 cycles of extension pulsing, and then it's going to stop. Just a few more cycles. Open up the sample slightly, and the camera takes a picture. Then once it processes the data, the test continues. Fatigue crack growth propagation test, we had the program set up so that it would take digital pictures of the crack every 100 cycles throughout the test. We ran strains at 5, 6, 7, 8, and 9%. We ran 10,000 cycles at 5% and 5,000 cycles each at 6 through 9%. This is a time-lapse video showing the propagation of the crack from the beginning of the test toward the ends of the test. You can see how it will grow across the screen as the test progresses. Once our fatigue crack growth test is finished, we have a raw data file. This is an example of the raw data file. It's just basically a comma-separated value file. And inside of that file we have identification of the particular test specimen, something about its thickness, something about its width, something about the height between the grips. And then we have a record of each data point by cycles. This would be 100 cycles, 200, 300, 400, so on, down throughout the test. The strain level, the input strain level, the actual strain level that was achieved, and then some other numbers that we'll talk about later. On the far right side, we have the actually the JPEG file associated with each photo that was taken of the crack. And so this is going to get lifted and dropped into an Excel program that will identify all the columns and then make it easier for us to manipulate the numbers and everything. But this is the next step. This is the raw comma-separated value data file. This is the next step in the data analysis program. We take the comma-separated value file and we drop it into an Excel program, which then identifies the data by column. First of all, we list the compound identification number, the dimensions of the compound, the conditions that were used, how many cycles were run at each condition, and the initial crack growth or crack length. We start and we also specify what the pulse conditions are. We have a 10 hertz Habersign pulse, 4 hertz rate, and the initial stress is 0 for each cycle. And then here we have our data columns. These are the cycle numbers, the strain, the input strain, the actual strain, the actual displacement when it's extended, and then the actual displacement when it's retracted. Okay, so this is coming back to a zero stress state, and then the loads at each of those states, the stiffness of the sample, the modulus, the tearing energy, okay, and the tearing energy, the unloading tearing energy in this column, the crack rate, and then also the actual crack length that's measured in this column. And so this data is how we drop everything in, and it's quite a long data file because it goes down for all the different strains. There's 5, 6, 7, 8, all the way down to 9% strain. So this would be typical of the data. Then the other thing we include is we include a digital image of the very last crack condition at the end of the test. This allows us to take a little bit of look at the crack as it proceeded across the specimen to make sure it didn't branch. Oops. And also we can get a good look at the crack tip as well. This would be the crack tip at the end of the test. Typically we run 3 samples, 3 replicates, and then we summarize those. So this particular summary page shows us here's each strain that we tested at. Here's the samples that we had, 2, 4, and 5. These are the crack growth rates at each strain, and then we can plot those. And generally we get pretty tight agreement among specimens, and if we have something that is an outlier, then we have a chance to run more specimens until we feel that we have accurate data representing the compound. This concludes our introduction of fatigue crack growth testing done at Experimental Services. We talked a little bit about the equipment that we use, how it works, the specimen, and some of the software that we use to control the test and analyze the data. This is just another powerful tool in our arsenal of test procedures that we can use to quantify material properties.